Look at this witch flying through the sky, leaving a trail behind. See that bell-shaped curve? This is called the Witch of Agnesi. The name sounds strange, but this curve begins with a simple circle, and later it leads us straight into the world of probability. But here is the twist. Although it looks like the normal distribution, it behaves very differently. Let's draw the witch. Draw a circle. Then at the tangent line at the top, now pick a point on the circle. Let's call it A. From the origin O, draw a line passing through A. This line cuts through the circle, and then continues upward until it meets the top tangent line. Let's call that intersection point B. Now we define a new point P. P is not chosen directly on the circle. Instead, it is built from two pieces of information. It takes the horizontal position of B and the height of A. So P is like a hybrid point, part circle, part tangent line. Now watch what happens. As A travels around the circle, B moves along the tangent line, and P moves with them. And as P moves, it leaves a trail behind. That trail is the Witch of Agnesi. Before we go further, let's talk about the name. Why is this curve called a witch? Maria Gaetana Agnesi was an Italian mathematician who studied the curve in 18th centuries. In her Italian text, the curve was called versiera, a word related to turning. That makes sense because this curve comes from a moving point turning around the circle. But later, in an English translation, versiera was confused with aversiera, a word associated with a female adversary or a witch. And so, by mistake, this curve became the Witch of Agnesi. It is a strange accident of language. Without this mistranslation, the curve might have had a much quieter name. But because of this mistake, the name became unforgettable. At first, this construction looks purely geometric. A circle, a tangent line, a moving point, and a trail. But every point in this picture has coordinates. So the question is, can we turn this drawing into an equation? Let the circle have a center at 0, A and radius A. Now we describe the moving point A using a single angle theta. Once A is chosen, the line from the origin is determined. That line meets the top tangent at B, and point P is defined by taking the horizontal position from B and the vertical position from A. So the whole construction can be written using the same angle theta. Now we eliminate theta. The moving construction becomes one fixed equation. After simplifying, we get y equals 8a cubed over x squared plus 4a squared. This is the equation of the Witch of Agnesi. Now let's take the simplest case. Set the radius of the circle to 1/2. Then the equation becomes much simpler. Fx is equal to 1 over 1 plus x squared. This is already a beautiful curve, but something even more interesting happens when you look at the area beneath it. If we integrate this curve from negative infinity to positive infinity, the total area is exactly pi. For a probability distribution, however, the total area must be 1, so we normalize the curve by dividing it by pi. So the new function is fx is 1 over pi multiplied by 1 plus x squared. Its total area from negative infinity to positive infinity is now exactly 1. And this normalized Witch of Agnesi is known as the standard Cauchy distribution. Now let's compare it with another probability distribution, the normal distribution. Both curves have total area 1. As the shade Shaded regions fill the screen. The accumulated areas approach 1. The normal distribution reaches almost all of its area near the center. The Cauchy distribution is different. A noticeable part of its area is still hidden far out in the tails. Once those distant tails are included, the total area also becomes exactly 1, so the witch has crossed a bridge from geometry into probability. Here is the normal distribution. It is the familiar bell curve that appears all over statistics. And here is the normalized Witch of Agnesi. This is the Cauchy distribution. At first glance, the two curves look surprisingly similar. Both are symmetric, both have one peak at the center, and both get smaller as we move away from the center. So, if we look only near 0, it is easy to think that they belong to the same kind of world. But now, watch what happens in the tails. The normal distribution fades away very quickly. The witch does not. It lingers. The reason is hidden in how the two curves decay. The normal distribution falls like an exponential function, but the Cauchy distribution falls much more slowly, like 1 over x squared. That difference may look small near the center, but far away, it becomes enormous. At x closer to 10, the normal curve has essentially vanished. But the witch is still visible. This is called a heavy tail. In other words, extreme values are not as rare as the normal curve would suggest. This idea also appears in the real world. For example, financial markets sometimes make unusually large moves. Large jumps and crashes may be rare, but they can happen more often than a simple normal model would predict. Some kinds of risk works this way too. Most events are ordinary, but a few extreme events can dominate the whole picture. The Cauchy distribution takes this idea to an extreme. And because of this heavy tail, the Cauchy distribution has no well-defined mean and no well-defined standard deviation. It looks familiar near the center, but if you follow its tail, you enter a very different world. A world where some of our usual statistical intuition breaks down. The Witch of Agnesi began with a simple circle. It became a witch through a mistranslation, and in probability, it becomes the Cauchy distribution. The witch looks like a gentle normal curve until you follow the tail. That is where the real differences lives. If you enjoyed this, there are many more shapes to explore. Please subscribe and let's keep going, because mathematics has a shape.